We are Group 59 and our product is Oxygen Candle Emergency Ventilator, or OCEV, that aims to accommodate the shortage of medical ventilators and oxygen supply, especially during this COVID-19 pandemic. My name is Nabil Iman and I'm the project director. And here is my team along with their roles. These are the topics we will cover in this video, presented by our team members. As we all know, Malaysia's healthcare system is collapsing and the COVID situation is continuously deteriorating with no signs of improvement. On top of that, the influx in infections are overwhelming hospitals and they have inadequate resources to handle the high volume. Due to the costly nature of ventilators and scarcity of medical oxygen supply, the OCEV can be a relatively low-cost, low-requirement alternative in emergency situations, as well as satisfy the medical equipment demand.
Hello, I'm Song Swan and I'm going to talk about the literature and design application of the OCEV. Through literature review, we have discovered two inventions with different purposes that can be integrated into an innovation that can achieve our objectives. The first invention is the oxygen candle. The oxygen candle is a solid form of sodium chloride which produces oxygen when heated at a high temperature. The second invention is the self-inflating bag valve mask. Bag valve mask is the current way of providing emergency ventilation to patients who require respiratory support. For design thinking application, 5 phases were used to help us create the design. The first would be empathize, learning about the audience that the product is designed for, define, analyze and identify the target audience needs and insights based on a survey. Ideate, brainstorming and producing creative solutions. Prototype, simulating one or more of the ideas to show the audience. And finally, test, sharing the prototype and generating users' feedbacks to establish new solutions.
Moving on to project planning, this section will cover planning, scheduling, flow, and task distribution. Here is our detailed Gantt chart that includes planning, scheduling, and task distribution. But in short, each member has their own roles and tasks which may deviate from their role. Next is the flow of the project that includes brainstorming, finalization, research, engineering, analysis, design model, animation, and final report. This ensures that the work we do are efficient and smooth.
Hi, I am Anis, and now we are moving to the methodology. Articles research had been made by the members where the works were majorly broken down into chemical engineering and mechanical engineering works. Second, after the researching, idea finalization had been made where here are the major parts decided. The oxygen candle is applying the reaction engineering where these are the chemical equation. Other than that, it was decided to use closed-loop stepper motor, lithium-ion battery, and the human respiration info had been found. Besides, we also had calculated several information such as the volume and flow rate of the oxygen production, flow rate needed by the patients, dimensions of the components, and Boyle's law principle is used to calculate the pressure required. Furthermore, this is the PNID which built using Microsoft Visio. The control system also included. In addition, Autodesk Fusion 360 had been used to build the OCAF 3D design. And last but not least, the simulation was done for the gear where static stress was analyzed such as the safety factor, displacement, stress, strain, and reaction force which can be concluded that the design is safe and convenient. For the design selection, this is our final design which consists of oxygen candle with case where the oxygen produced, compressor to compress the oxygen into lower volume, oxygen tank to store the oxygen, humidifier to add moisture into the dry oxygen, BVM act as the ventilator, BVM support, mechanical pedals to squeeze the BVM, control panel display the readings, battery box and caster wheels for the movement. The other components were purchased, however BVM and oxygen candle casing were fabricated.
Hi, my name is Fazil Fakri and I'll be explaining about the design concept part. So this is the final design of OCEV. As for the dimension, the overall height of OCEV is 1.47 meter, which is the child's level for average people's height, so it can be operated conveniently. As for the oxygen candle, the casing diameter is 0.05 meter with height of 0.2 meter and volume of 19.24 liter, and the overall height of the casing is 0.51 meter.
Now I'm going to explain on the working principle of the OCEV. Specifically here shows the oxygen candle and the candle casing. So how it works is, in order to start the process, we will first require inserting a red phosphorus pin into the firing pin, which will basically create a spark to ignite the iron powder present in the oxygen candle. This will allow heat to be generated and allows the reaction of decomposition of the candle to occur. The reaction will occur under atmospheric condition, and when oxygen gas is produced, it will flow through a tubing towards an oxygen storage. But before that, the oxygen gas will also pass through a filter to remove any impurities. For safety reasons, there is also going to be a pressure relief valve on the casing. Here's the model for the compressor and pneumatic valve, which are both controlled by a controller. When the pressure exceeds the atmospheric pressure, the pressure transmitter will send a signal to the controller, which will signal the compressor to start and the valve to open. The oxygen gas will flow at a rate of 66.82 liters per minute, and the working pressure of the compressor will be at 222.73 bars. So once the reaction finishes, the pressure in the oxygen case will return back to atmospheric condition, and then once again transmitter will signal controller, which will signal compressor to stop and the valve to close. Now I'm going to explain how the oxygen is stored in the oxygen storage and how it will be transferred to the BVM. So actually this is a two separate process. Only one tube will be connected to the storage at a time. So the first tube will be the tube containing the pneumatic valve from the compressor, which basically transfers the oxygen produced to be stored in the oxygen storage.
Once all the oxygen is stored in the oxygen tank, the compressor tube will be removed and the tube from the BVM will be connected to the oxygen storage. The BVM tube will include the pressure regulator to control the output pressure of the oxygen gas. There will be also a flow meter to adjust the flow rate of the oxygen gas using the manually controlled valve. Before the oxygen gas from the storage enter the BVM, it will pass through the humidifier, and the humidifier will cool down the temperature of the oxygen gas. This is the model of the BVM that hasn't been compressed. What happened here is the humidified oxygen gas will pass through the oxygen inlet valve and enter the ventilation bag. Any excess oxygen will be stored in oxygen reservoir bag. Once the oxygen passes in the ventilation bag, there will be a mechanical paddles alongside the bag will compress it and push the oxygen into patient's airways. And the pressure and oxygen concentration sensor is basically part of the control system that controls the rate of the mechanical paddles compressing the ventilation bag. Basically, this is how the mechanism of the gear and the motor to drive the mechanical paddles. The mechanical paddles will compress the ventilation bag and push the oxygen into patient's airways.
Hi, I'm Mahani, and now we'll be moving on to our results and discussion. Firstly, the main aspect where our design consideration is most significant is the calculation results in determining the oxygen candle specification. As summarized in the table here, it is noted that all these values are considered in order to suffice for at least an overnight duration. More specifically, our OCEV is estimated to last for at least 8 hours and 50 minutes. Considering that a severe pneumonia patient requires 12.6 liters per minute oxygen on average based on our literature research. Besides, the capacity of compressor used for OCEV has also been determined in order to suitably compress the oxygen produced by candle into a 30-liter oxygen storage tank. Then, in regards to the gear simulation, we have generated the following results for the static stress analysis as obtained via Autodesk Fusion 360. Based on literature research of recommended force to be exerted in compressing the BVM, we have conducted the simulation while considering the maximum torque estimated per mechanical paddle. Hence, inclusive of the design gear ratio, we arrive at a maximum momentum load of 12.5 Nm applied at driving gear. There are currently no signs of expected gear pitting due to extreme surface fatigue failure of gear tooth. This demonstrates greater reliability of the compression mechanism used in OCEV, as the reduced risk of material fatigue adds value to the aspect of less maintenance desired.
Vigorous research was done in order to identify the best possible materials needed in making the OCEV cost efficient. As seen here, the price for each main components involved in producing the OCEV has been summarized in the table, where costs in purchasing items as well as manufacturing and labor work are all included. Through our estimation, the total cost in manufacturing OCEV is approximately 9,000 ringgit. Therefore, the OCEV selling price is proposed to be 10,000 ringgit per unit. By comparing our product with the average cost of currently existing medical ventilators, which are usually around 100,000 ringgit per unit, it is noted that the OCEV has significantly enabled a 90% cost saving.
Next is a survey analysis for OCEV itself. The reason we conducted this survey is to better understand the needs of our targeted users comprising of medical sector workers, which will help us produce a more viable solutions towards the issue at hand.
In conclusion, OCEV is an idea proposed with the objective of sustaining ventilator and oxygen tank shortage that may occur as a result of the constantly increasing of COVID-19 cases, as well as any future hypothermia-related emergency situations. Therefore, OCEV has potential to be commercialized as it can serve as the alternative to satisfy the current and future ventilator and oxygen tank demands. The recommendation to improve the functionality of our prototype is we can add auto switchover to battery backup so that the mechanical BVM can be functioned without disruption once the main battery is low. Next is a safety alarm, which will notify the person in charge if there are any mechanical issues occur. That's all from us. Thank you.